Okay, so we're now going to go back and look at the other types of nonlinear neighborhood operators which cannot be represented by convolution. I've only selected the ones that I think are most useful practically. So in other words, those that I think are in wide use. I mean, you can find a lot of mappings that produce an output value in an image based on the values in the neighborhood of some location in the input image, and using really weird, bizarre, all sorts of varied mappings between that collection of pixels you have in a neighborhood of an input pixel and the value you map it to. So you can imagine lots of different things that could be done. So I'm restricting the discussion around this to those that are most useful. And the first of those is median filtering. And I mention median filtering because if you're working in the field of medical imaging, either in X-ray imaging or in, let's say, one of the exotic nuclear medicine domains, where you often have quite a lot of noise within the image because you don't want to image for a long time, because you have constraints on the dosage you give to the patient, for example, then in those settings you often have lots of variability in the image and lots of specifically photon noise, because imaging using in some domains is very much dominated by the quantum nature of electromagnetic radiation. So median filtering is something that can be applied in those settings. It also is useful if you have microscopy images where because of the resolution you're trying to get out of your microscope, you might be pushing the microscope really hard and getting very, very low photon counts at your sensor level. And in that setting as well, the median filtering is useful. So the basic idea is to run through your image, just neighborhood by neighborhood, just as you do with convolution. But instead of using sort of multiplications and additions, what you do instead is you grab your collection of pixel intensities in a neighborhood, sort them from the lowest value to the largest value, and find the median value between those two. So that's the sorting operation. And the sorting operation can either be a median that's computed by the just using the range of values, or actually so using the range, or actually listing the pixel values out and selecting the one that's in the middle, which is a slightly different argument. So the median pixel value is mapping an image neighborhood to its median pixel value is really good at reducing shot noise without introducing too much blurring. The reason being that so there's a trade-off usually, and the spatial blurring tends to be a bit less in median filtering compared to something like a sliding averager. So median filtering is useful in that context. Okay, the next thing that I'd like to talk about, just jumping forward here to our morphological operators, is a bit more. So median filtering is just one. Based on a weird. Okay, right. So that should be based on mathematical morphology. So the basic idea of mathematical morphology, and in particular the morphological operators, is that they, rather than using addition and multiplication as the, let's say, the fundamental operations used to map neighborhood values to an output, the morphological operators instead use set theoretic concepts in order to map the input values to an output value. So the operators that we're going to describe are really very important in the context of binary image processing. There exist also grayscale morphological operators, but they are far less used for practical image processing. They can be used if you want to have weird filter effects, for example. So if you want to, create a rival to Instagram and you want to put these so-called filters on, then the grayscale or color morphology filter operators are useful. I'm not interested in that, so let's look at the binary image morphology and see where it comes from. So as I mentioned, we use set-based operations to define morphological neighborhood operators. So I'm finding lots of typos in my slides for some reason, and I can't understand why I don't see them in the lecture notes. So maybe they are in the lecture notes. I'm just not finding them. I need to upgrade my spell checker. So we're not going to talk about the grayscale morphological operators. We're going to start with the binary operators. So what we're going to do is to start off by saying, let's imagine we have two images. So one of those images is going to be the image that we want to do something with. So it's a leaf on grass image or whatever. And the other operation is going to be what is called a structuring element. So B here is often known as the structuring element. My pen is playing up. Okay, structuring. Oops, R-I-N-G element. It's not just it's a bad term for it, calling it a structuring element, because the and actually that term is quite common, particularly if you use MATLAB. You'll see that there's the MATLAB version of binary morphology refers to the examples often use SE, but both of these are actually sets of pixels. So if we restrict ourselves to binary images, then what we can do is we can form a set that represents our binary image by listing the elements in that binary image that take the value of 1 and assume that everything else is 0. So if you consider the set of pixels like this, 1 0 1 1 1 2 2 2 0 3 and 0 4, then what you might be considering, and let me just jump to my board to look at these. So 1 0 1 1 1 2 2 2 0 3 0 4. Okay, so let's make a binary. Let's make an empty image matrix and drop these things in. So I have values that seem to go from 0 to 4 in that list. So what I'm going to do is to make, let's use this thing here. So let's make a little image here. That's going to hold these things, image array. So 1, 2, oops, 3, 4. So I think what I'm going to need is I'm going to need to have 4 lines along here so that I can have 0 to 4, which would be 5 columns, and I'll give myself 5 columns and 5 rows. So that's going to be 4 of these. So let's do okay. So let's do it like this. So 1, 2, 3, 4. So it's going to be slightly wonky, but it's not too bad. And I'm going to do here 1, 2, 3, 4. Oh, that's very wonky. Anyway, it'll do. So let's pretend that this is our binary image grid. And so the elements that I'm going to give 1s to and everything else will be 0 will be 1 0 1 1 1 2 2 2 0 3 and 0 4. So let's drop those in. Just make sure that I'm actually on the Right, so I've been talking to you and been talking through this and not showing you what I've drawn, so apologies for that. So here is what I've drawn. Okay, it's a bit wonky. Sorry about not showing you that, but it's pretty obvious what it is. Okay, so that's our image, and we want to put elements in 1, 0, 1, 1, 1, 2, 2, 2, 0, 3, and 0, 4. So let's do that now. So this is going to be, this is 0, oops, it's going to be 0. This is 1, 2, 3, 4, and we're going to have 0, 1, 2, 3, 4. And so we're going to put, so element 0, 0 is going to have a value of 0 because it's not listed in our list of pixels which have a value of 1. Pixel 1, 0, 1, 1, 1, 2, 1, 0, 1, 1, 1, 2 all have 1s. So 1, 0, 1, 1. So 1, 0, 1, 1, and 1, 2 all have values of 1. 2, 2, 0, 3, 0, 4, 2, 2, 0, 3, 0, 4. So 2, 2, 0, 3, and 0, 4 all have values of 1. And so I've got value of 0, 0 here, everywhere else. Okay? So this is going to be my, my input image. This is going to be my A. So this is going to be A. Okay, so what you see we've done is we've represented the pixels that have 1s by this set of pixels, of pixel tuples here. They're basically coordinates where we're going to find 1s. We also have a structuring element here, B, which is 0, 0, 1, 0. So let's make a B so we can run through this example. So this is going to be, we don't need many elements here. So here's B, and let's just make B well, I've made that a bit big. Crazily big. Anyway, so we've got elements 0, 0, and 1, 0. So we don't what's happened there? We don't actually need to have lots of zeros representing B. Well, actually, maybe I should do that just to illustrate this a bit better. Okay, I'll do that. So I'll make this a bit bigger. So let's put another line here, another line here, and okay, so here's my B, and the only elements I have that are going to be 0, going to be 1, are going to be the two elements that correspond to 0, 0, and 1, 0. So there's and 1, 0, which is this one here, and then everything else is 0. Okay, so if I have this structuring element and this this definition of A, then the dilation of A by B is given by treating B as a translation and applying this translation. So it's actually not a translation, it's a set of translations. So we have two translations. One translation is by 0, 0, and the other translation is by 1, 0. So what we're going to do is we're going to apply these translations in turn to each of the elements of A. And what that's going to achieve is it's going to introduce new elements into the so if we create a set that contains the result, an empty set that contains the result of A dilated by B, then that empty set then gets filled as we apply these translations in turn to each of the elements of A. So if I translate 1, 0 by amount 0, 0, I get 1, 0. And so 1, 0 becomes part of the dilation result. If I apply 1, 0 to 1, 0, again, I treat this as a translation, then that, the 2, 0 becomes part of the translation result. So there you have it, there's 2, 0. If I apply 0, 0 to 1, 1, of course, I'm just going to give me 1, 1. If I apply 1, 0 to 1, 1, I get 2, 1. And so I keep on applying these as translations, which just means I add them. So I treat this as a vector operation where the vector is just a summation of the coordinate locations of elements in set A, non-zero elements in set A, and non-zero elements in set B. Yeah, or I should say non-zero elements in image A and non-zero elements in image B. That is, elements of set A, and then translate them by the elements of set B. And so that gives me all of these pixels down here. So the result of that is going to look like this. Oops, let's come back to this. So the result of A dilated by B is going to be, so let's draw another, let's make this a bit smaller. Okay, hopefully you can all see this. So let's make our matrix here, image array here rather. So there's one. Okay. So here are what the elements are going to look like, or the dilation is going to look like. So what we have is 0, we will have 1, we will have that element there, which is 2, 0. We'll have a 0 here, we'll have 1, we'll have a 1 here, we'll have a 0 here, a 1, a 1, and a 1. We'll have a 1 here, and a 1 here, a 1 here, and a 1 here, and then 0 elsewhere. Okay, so if you've if you've watched me doing that, it might occur to you that I haven't actually swapped back to look at the results that I've got back here. 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. Okay, but I'm fairly confident that I've got that right, because the way that you can do this is actually visually. So in that operation of adding those elements as translations, I can sort of geometrically figure out what's going on there by taking this pattern of 1, 1 and placing what I'm treating as the origin, which is this pixel here, over every 1 pixel that I have in here. So there's a kind of a way to think about this intuitively, as a kind of intuitive operation. So if I treat this as being the origin of my my structuring element, so origin, and if I treat different areas of B as being the origin, I'll get a shifted result. But usually I take a relatively sensible approach to defining where the origin is. And if you look at past exam papers, I either define the origin for you, or I expect you to say something about where the origin of the mask is. So, because you get different results depending on where the origin is. But the different results are just going to be shifted relative to what Yeah, if you shift the origin, you just shift the result, the spatial pattern. So how do we do this? So you just imagine you place the origin of the pixel of this mask over every one pixel in the image A, and then see where all the other non-zero elements of B fall, and append those in to the result. So here, if I place this origin here, that value of 1, that pixel there, falls here on this guy. So I take the union of the set of translations of element locations in pixel A by element locations in pixel B, where element locations refers to the non-zero element locations. So that pixel falls there, so it gets included in the set in dilation. When I place the origin here, that pixel falls there, so that gets included in the set. And so there's kind of a nice spatial fattening that happens based on it's in a direction that corresponds to the shape of the non-zero elements in mask B. Okay, so if you didn't get that, run through what I've said again slowly slowly. It was slow anyway. So run through it a couple of times until you see what's going on, right? So I'm basically fattening all the 1 elements of A in a manner that depends on the shape of the structuring element B, right? So the zeros don't matter, only the locations of the 1s matter. So run through that, make sure you get the idea. And it's sometimes described as the dilation operation is sometimes described as the union of all of the translations of elements A by those of structuring element B. Union of all translations. That's a typical phrase used to describe dilation. Okay, so now in addition to dilation, we also have so dilation generally fattens the white regions of an image. And so here's an example of applying dilation, and the shape of the structuring, the non-zero elements in the structuring element, there's the overloaded word element, the shape of the effect depends on the shape of the structuring element. So if we dilate with a 3x3 structuring element of 1s, for example, so everything is equal to 1, this is your input image, this is what you get. So you get a fattening and a filling of all the holes inside the leaf regions. But you also get this downside, which is that these pixels out here in the background, which are sort of, you can think of them as noise due to the thresholding process to create the binary image in the first place, they get fattened, which is probably not a good thing. And then I've also repeated that in going from here to here, so from the original binary image to this one, by dilating with a different shape of structuring elements. So a shape in which you have a 3x3 structuring element with 1s along making a sort of a plus shape in the mask. And that's what you get as a result. So again, here you've got a nice filling in of the holes in this interior region, but you also get this fattening of the noise pixels in the background according to the shape of the structuring element. So in addition to dilation, there's also something called erosion, and I have to say that there are different definitions of erosion in use. It's a bit like convolution in some ways, which is that convolution, strictly speaking, should involve a flipping of a mask. And sometimes in implementations of convolution, for example, in the framework PyTorch, the convolution routines don't flip the mask, which is an error in the implementation. Whereas in TensorFlow, the convolution operation flips the mask. So strictly speaking, the mask should be flipped in convolution. In erosion, you can either have flipping or not of the structuring element. So what I'm going to use is the definition I give you by example here, which is that what you do with erosion is that you apply the translations in a similar way as you do for dilation between the structuring element and the image you want to dilate. So this is now, sorry, the image you want to erode. So this is now erosion. But erosion is kind of a test to see if the translations supplied by structuring element B to the elements, the non-zero elements of A, result in elements that are already in the set A. If they do, then you keep those elements. But if they don't, so if the translations push sort of fall outside the elements that are already in A, then you don't include that particular location in A. So that deserves a bit of a careful looking at. So let's have a look at this example here, where I go through an erosion. And the first thing to note is that the result of erosion is smaller in terms of the number of elements in the set than A. And the way that we get to this result from this starting point of A and this starting point for our structuring element is we test each of these translations, we apply each of these translations, and we test them to see if applying a translation of 0, 0 to, let's say, 1, 0 results in an element or location that's already in A. So we do that, and because these translations are 0 rows and 0 columns, then applying that translation to 1, 0 will result in 1, 0. Well, 1, 0 is already clearly in set A, so we don't need to, so far so good. We then apply translation 1, 0 to element 1, 0, and that will give us 2, 0. So let's just write that down, 2, 0. Okay? So we test to see whether 2, 0 is in the set A. It isn't. And so that means that this translation, or this structuring element here, when we apply this as a erosion operator to A, it turns out that the translation supplied by 1, 0 does not result in 2, 1, 0 does not result in an element that is already in this set. For that reason, or given that, we do not include 1, 0, because in a sense, in applying the structuring element B to that element there, it doesn't give us a result under translation that is already present in the set A. So that's the definition of erosion. So the translations of B must all result, translations of B apply to each element of A. So each of these translations apply to each of these elements must result in an element that's already in A. If it doesn't, then we don't preserve that element in A. And so the effect of that is that 1, 0 gets removed from the result, because that guy there, translating that by 1, 0, gives us 2, 0, which isn't in this set. And that's it. So that's how we do we do that in very simple terms. And we repeat that process for each of these elements here with each of these elements here. So 1, 1 translated by 0, 0, of course, is 1, 1, which is there. So just hold that thought. Then apply to 1, 1 the translation 1, 0. That gives us 2, 1. 2, 1 is also not in the set. So that also gets removed. So that gets removed, that gets removed. Let's try 1, 2. So apply 0, 0, of course, 1, 2 is here. Apply 1, 0 as translation. We get 2, 2. That's not in this set, so we get rid of that. 0, 3. Apply 0, 0 as a translation. Of course, 0, 3 is there. Apply 1, 0 as a translation. We get 1, 3. And 1, 3 is already in this set. And therefore, this guy gets preserved. Okay? If we repeat that process to the remaining elements, 1, 3, 2, 3, 3, 3, and 1, 4, you'll find the only ones which under translation by 0, 0 and 1, 0 result in an element that's already in here are 1, 3, which is that guy there, and 2, 3, which is that guy there. And so the other two also get removed. And so you end up with this as a result. If that bit hasn't made sense to you, replay it. I'm sure that you'll see what's going on, because it's really pretty simple. What does it look like? So here is, I've got both an erosion here and a dilation going on. So in the first case, I've still got erosion followed by dilation. That's not right. That's dilation followed by erosion. How silly. Okay, dilation followed by erosion. Okay, so what I've done here is taken this as our image, and this is our structuring element, and here I've applied first of all a dilation, and so this dilated by that gives me that, and then I've applied an erosion, but in applying the erosion I've applied a negative erosion. So I've flipped the mask before I've applied the erosion. And I've done that deliberately because this example is perfect to illustrate something very important that you must remember, which is that dilation followed by erosion using the same structuring element, which is, you can see it's the same in both cases, although one is a fattening operation and the other is a sort of a thinning operation, as you can see from this case here. So we've gone from that number of elements, which is 8 elements, down to 3 elements. That effect of erosion is not the inverse of dilation. So if we dilate this by this, we get this. If we take this, shift it up here, treat this as now our input. So let's think about having a line down here, okay, just to make that crystal clear. These are two separate things. But what I've done is I've deliberately taken this image here and treated this as the input here. Okay, so I hope that's clear. And what you see is that although this shape looks, pretty similar to that one, what we started with, there is a translation. And so I like this result because it's very simple to try yourself and figure out how it works. And what you see is that the dilation followed by erosion does not necessarily give you back the original result. So the two are not inverses of each other. You can think of them as duals of each other, but they are not, in the sense that one fattens and the other shrinks, but they are not inverses. Okay, so now the way that geometrically you can look at how this has worked, at least in the illustration I've done here, what I've done here is flip this around, done the sort of convolution style thing. And I want to make it very clear that there are different definitions of erosion around, which either flip or don't flip. But what I've done here to sort of illustrate what's going on is you basically flip this around. So this guy goes over here, okay? And now think about, so what you have is, so you have a 0 there, and you have a 1 here. And in lots of books on erosion and dilation, the black locations represent 1s, and the blank locations represent 0s. So in particular, if you look at some of the foundational literature on dilation and erosion, you'll find these kinds of representations all over the place. So I'm introducing you to those here. You now basically place, so this is the origin indicated by the dot. You place the dot over every location here, and see where the other element falls. So in this case, what I'm actually doing is placing, if I flip this mask, or flip this structuring element, it looks like this, with the origin being here, with the origin being this guy here, right after I flipped. And so if I place this so that this origin lies here, that pixel falls outside of the other regions containing the dots. And so because the mask doesn't fit fully inside the region, when the mask origin is placed here, I eliminate this point from my output. I then place the mask here, so the origin is here, and that pixel now falls here, that pixel now falls here. So both of these both of these dots are falling over dots already here, and so we preserve this location in the output. I repeat that repeat that shifting of the dot to every location that has a dot, and do that test to see if these two dots fit inside dots that are already in my set to be eroded. And when I do that, the result, and if so, I preserve the position of that origin. If not, I remove it. And so at the end of that process, I get this. And so that's, and you can imagine that I would get different results if the mask had different shapes. So the structuring element had different shapes. So please try that, make sure it makes sense to you. You can ask yourself the question, what would the result be if you didn't flip the mask as I've shown here? So I've deliberately left this in because I want you to think about this and resolve this in your head. But I've also left it in because it illustrates, as I said, the important point is that you can't guarantee that erosion followed by dilation will return you the original result. And this illustrates that point perfectly. So let's now look at applying erosion followed by dilation. So in the first case, in these two images here, so A and B, so this is erosion, and this is erosion with a mask that's where the structuring element, sorry, I call it a mask, but the correct word is structuring element, ironically enough, is just binary ones in this shape. Okay, so it looks like a sliding averager, but of course you're not applying this using multiplication and addition. You're actually doing it using the set theoretic operation. So your structuring element looks like this. You apply that to your leaf on grass image, and this is what you get. So the good thing is that you've got rid of all the background noise here, the small pixels that were sort of just one standing out in the middle of the sea of grass, or the sea of zeros. You got rid of those, but you've also made big holes in your leaf, so that's not so good, right? And erosion applied with a structuring element of that looks like a plus sign, so it looks like this. Let's get this drawn in here. So it looks like 0, 1, 0, 1, 1, 1, 0, 1, 0. So it looks like that. So a little plus sign gives you that, unsurprisingly. Again, you get rid of the noise in the background. So tantalizingly interesting, but you get these big holes here. Now, if you apply erosion followed by dilation with the same structuring element, look at this. You kind of get rid of some of the actually, this is dilation followed by erosion. I apologize, it's not erosion followed by dilation, because we have so erosion followed by dilation is this one over here. So let's just make that clear. So this is this. Now this should have been erosion and dilation. This is a bit misleading. Whereas here, what I've got is I've got so this here is erosion first. Sorry, dilation first, followed by erosion, and this is erosion followed by dilation. Okay, so you can see that this gives us a nice interior but leaves us with some fattened noise pixels outside. Whereas this, the erosion followed by dilation, gives us a nice perfect outside, but then we've got some holes that have opened up here. So for both this case and this case, I've used a 3x3 structuring element, and you can see that effect because here you can sort of see that blockiness that's cropped up in the result of dilation followed by erosion, so that you can kind of guess that it's a big blocky thing that I've used to do this. And here, where I've applied erosion first followed by dilation, you can see that that blockiness becomes really exaggerated. But the nature of this with the erosion is that I've actually got rid of some of the fineness around here, the shape of the tip of the leaf, in doing the erosion. And when I've then done the dilation, it's kind of made this big blocky point to the tip. So just to stress again, this is by doing dilation first. Let's just write it down here. Oh, God. Dilation, then erosion. Sorry, my pen is really playing up, which is very annoying. And then this is erosion, then dilation. Okay? And in both cases, I've used the structuring element of this guy up here. Okay, so this is kind of so tantalizing because in this case I have no holes, but I got some blockiness here. And here I've got holes, but I've got rid of all the noise in the background. So this is kind of feeling really close to being wonderful. And it turns out that if you combine dilation and erosion operations in the right order and the sort of right combination of structuring elements, then you can define lots of other sorts of processes. So you can use to express something called the hit and miss transform, skeletonization, and also you can use erosion and dilation for noise removal, as suggested by the previous examples. And there's one particular combination, which is opening and closing, where if you apply successive opening and closing operations, you can get really, what some people call perfect filtering, which is not, it's a bit of a misnomer, but it does work in some cases. So binary opening is defined like this. So that's the symbol for opening there, and K is the structuring element in this case. So and the opening of image A with structuring element K, again in the binary context, is defined as the erosion of A by K, and taking that result and then dilating it by K. So this can be thought of, it has a sort of a visual effect, or you can sort of imagine what this looks like. If you take the structuring element K and sweep it around on the inside of the region of white pixels of image A, so that you don't extend around the boundary, and wherever the structuring element doesn't fit, you sort of fold the boundary of A around the structuring element. And we'll come to some examples in a second. The closing of an image A with structuring element K, conversely, is expressed in terms of the first of all, so this represents closing here. That's closing. Closing. And that to do that, you first take the complement of the elements, the complement of image A, which means you flip all the 1 pixels to 0 pixels and flip all the 0 pixels to 1 pixels. So you flip the values of the pixels. So something that's a solid blob becomes a solid hole, if you like. And you then open that with a reflection of structuring element K. So reflection means you flip around the coordinates as you would in doing convolution, but it's called reflection in this case. And then you take that result, the opening of that, and you take a complement again of the result. So Now this can be viewed as taking your reflected structuring element and sweeping it over the exterior of a boundary, and then smoothing the boundary from the outside rather than from the inside, or the boundary of a binary shape. So this is what opening looks like using a solid structuring element of ones. Okay, so here's our leaf on grass image with a thresholded, and this is the result of opening, and you can see that it's actually done a really good job of getting rid of all of the noise in the exterior. And the interior, which had holes, still has holes, but the holes haven't really grown very much in shape. They've changed shape to some extent, but they haven't really grown very much. So that's getting closer. Now, if we do an opening followed by a closing, and in both times using a solid structuring element of ones, this is what you get. So you go from, so this is the leaf on grass image when it has its holes. So this one, after you've done an opening followed by a closing, and this is closing followed by opening, and this is opening followed by closing. So here, almost perfect, but you got lots of noise. Whereas here, so just switching the order of opening and closing around, you get pretty much what you might call a perfect result, which is that there's no noise pixels in the exterior, and the interior of the leaf has no holes. You can see, however, that there's a bit of distortion to the boundary, and depending on which of these operations you use, which one you consider worse. So for example, this one here has a pretty nice pointy edges to the leaf, and this one has sacrificed a bit of that in order to get an otherwise perfect result. So and you can see little sort of signs of the shape of the structuring element that crop up here and there. So your boundary shape gets distorted in doing this, but still it's not a bad result if you just want to get rid of noise and fill holes. So again, closing. This is closing the binary leaf image. Oh, sorry, I said closing followed by opening. This is just closing, and this is opening followed by closing. So apologies, I said this was a combination of operators. It wasn't. It was just closing, and this is opening followed by closing. So in other words, do this, opening, and then close, and you get this. Okay, so apologies if I've caused confusion there, but you can read what's there, and hopefully you heard what I said towards the end, which is a kind of autocorrect that kicked in a bit late. Okay, here is the result of closing followed by opening. So it is on the other page, so you can see you can compare this result with this result. Okay, and hopefully if you go back to the lecture notes, you'll see that the things are a little bit more organized in the lecture notes, the printed lecture note, or the big document lecture note version. Okay, this is known as a top hat transform, and this result here, and you can see that what it is the absence of the leaf, but preserving all the fine regions of the background. So it's like a perfect high-pass filter. You've got rid of the big structure in the image, you're just left with little regions containing detail. So that's this is known as the top hat transform. Okay, now grayscale morphology is not something that we are going to consider, or it's not examinable. You've got a section on grayscale morphology in your lecture notes, so you can read through that and see how it's used. You'll see that there's also fattening or thinning of objects in grayscale images, but the fattening or thinning is also dependent on the intensity or the gray level value of the particular structure you're looking at. So it's kind of a shape and intensity based operator. Okay, so that's chapter 4 is a little bit longer than it should have been in terms of lectures, not helped by having slightly wonky sort of technology on my side, but I just wanted to look at what consider what we've looked at here. So we've looked at two main categories of neighborhood operators, linear and nonlinear. All the linear operators can be implemented by spatial convolution. And by the thing you realize is that if you implement a convolution operation, you can then change the effect of that convolution operation. First of all, by changing the mask values. So you can like define the function to do convolution between image and mask. Okay, and once that's defined, just by changing the values in the mask, you can get different results. So you can smooth the image, you can estimate gradients in the image, you can estimate second derivatives, you can do all sorts of weird and wonderful things. So you have a lot of flexibility with the linear convolution operators. We've looked at, so we spent more time on linear operators because getting an intuition about what convolution does is quite important. We've considered a few implementation issues, the issue with the border effects in the image, the array, image array, and the computational cost, and we've looked at the savings you get if you use separable convolution masks. And we've introduced nonlinear operators, both by applying activation functions to convolution. So convolution, so just a reminder, convolution followed by activation function you can think of as being a convolutional unit, which is the term that's used to describe these artificial neurons in deep neural networks. So just thinking about those two parts is really useful. And we've also looked at a couple of nonlinear operators apart from that, which don't use convolution, which are the median filtering. As I said, very useful if you've got to do pre-processing of microscopy or X-ray image data, and also looked or introduced binary mathematical morphological operations. So that concludes what we need to do for chapter 4.